This is really, really cool stuff. It's called linear regression, and it's how we can fit data and create a best fit line. So say we had a bunch of data here. Why don't you go ahead and just click them closed for a second. Just be ready to pop them open though and do some stuff. We could plot this data, right, on a graph where, let's say, we let T be the horizontal axis, normally the x-axis. So those would be my input values, and V would be the output values. And that makes sense because look what we're analyzing here. We have an object's speed or velocity recorded at various time intervals. So the input variable goes with the independent variable, right? The output variable is the dependent variable. Wouldn't it make more sense to say that the speed depends on the time than the time depends on the speed, right? We're inputting, for various different values of t, we're measuring what the speed is. That's the interesting variable to us, is the speed in this case, right? So that's the dependent or output variable. We could plot these things and make a scatter plot. Give me 1 to 5 on how much you remember about that. You could just plot ordered pairs and they each correspond to a point, right? And we'll look at a representation of that on Desmos here in a second. In fact, let's do that first. In Desmos, let's create a scatter plot. I'm going to show you how to do this. It's really simple. Very powerful tool. I'm going to make that a little smaller so we can see both. So everybody bust out Desmos graphing. Okay, and if we want to make a table, here's what you do. You go up to the add item, the plus symbol in Desmos graphing, and what do we choose? Table. There you go. We choose table. And notice it puts at the top of the left column, it makes a t-table, and it says x1 at the top of the left column and y1 at the top of the right column. You can leave those as x and y if you want to. It's fine. If you would like to, you need to leave the 1 there, though. That sub 1 means that this is a list of data. These aren't variables. These are data points. So that's what you got to leave that subscript there. I'm going to change this to match what we're dealing with in this application. So our input, instead of being x, is t. So I'm just going to replace I'm going to make it a lowercase t. We're going to make that a t1. And the output, let's make v1. But you don't even really have to do that. You could leave it x and y if you want to. And then we're just going to record all that data, right? So the input, the t values are just 1. I'm going to hit the down arrow, 1, 5, 6, 11, 14, 15, 20. And then I'm going to pop back up here and I'm going to put in the corresponding values for V. Why don't you do the same? Oh, what happened there? Oh, okay, I see. I messed that up. That's 6, 11, 14, 20. There we go. Okay, so there's my data table, right? Now, if you want to see what this looks like, I can go over to the graph and look, I can see one data point there. If I click on it, look what that is. It's the ordered pair 1, 3. And as we've mentioned before, data tables are really, t-tables are handy ways to write data, because then it looks, if I read left to right, they just look like ordered pairs, right? So there's the ordered pair 1, 3, and there's the point. If I zoom out, I can see all those. But instead of having to fit the window, like if I zoom out, they may not look that great. They're all kind of bunched over to the left. Whenever you input a data table, Desmos gives you a really handy option. If you click on that little magnifying glass down there where it says zoom fit, it'll resize the window perfectly so you can see the data really well. Okay, so give me thumbs up if everybody's there. Okay, everybody's there? Good. All right, so next issue. How do we fit that data? Does it look linear to you? I mean, it's not perfectly linear, is it? Right? It doesn't fit onto one exact line. If I were to connect all those dots, I would create kind of a jagged pattern, which isn't much use to us mathematically. We want to find some function that's going to be easier to work with. And so even though not all the points lie on exactly one line, wouldn't you say that the distribution looks like it has a linear pattern? Would you agree with that, everybody? You see what I'm getting at? I mean, it's like I could kind of visualize that there is a line that I could draw in there that matches that distribution of data, right? Did you ever do any of that in the past? Did you guys ever draw best fit lines? Give me Say it again. In chemistry, okay. And you did it by just kind of probably using a ruler and how did you go about that process? Like what are the things I would think about if I were trying to draw a best fit line? Okay, so I want to be, what do you mean by that? Okay, I want to draw it where the points are, the most of the points would be close to the line. What else? Okay, what about outliers? Which ones are outliers and maybe don't pay as much attention to those? Okay, what else? These are all good things. Do I want to draw it so I could have maybe, like, would it be okay to have most of the dots below the line, the points below the line, and not very many above the line? Is that okay? If I'm trying to find a best fit line, don't I kind of also need to make sure that I've got about an even number of points that are sitting above the line and below the line, roughly, right? Okay, those are all exactly the things you'd want to think about. Now, let me ask you this. If I gave each of you a piece, like a transparency, and you were going to put this down on top of, let's say this was on graph paper, and I was going to have everybody draw their interpretation of the best fit line, and then hand me all the transparencies, and I lined them all up, would they perfectly overlap, you suppose? Probably not, right? So does this seem kind of imprecise then? I mean, this is sort of a human judgment thing, and that's really not the way math should be, right? Don't you agree? Doesn't this rub you the wrong way a little bit? It does me. That there's, it shouldn't be like that. There should be a best fit line. There is. There is one best fit line, and here's how you find it. You don't do it by drawing it freehand. That's really just kind of a waste of time. So what you do in Desmos is we're going to do what's called regression. Okay. Um, you know what? I'm going to change these back to X's and Y's for this example. And you'll see why here in a second. It doesn't really matter, but just so whoops, there we go. And if I want to recreate, if I want to type Y1, I just type Y and a 1 after that. And Desmos knows to make that a subscript, to push it down. Okay, so the equation of a line is y equals mx plus b, right? In slope-intercept form. That's what we want to fit. I want to use this data, though, to do something other than just graph a line. I want to ask Desmos to use the list of values in the x1 column and the list of values in the y1 column to fit a line. So here's how I do that. Instead of writing y equals mx plus b, I'm going to write y1, which indicates that I'm using data. And look, if I type y1 in there, look what Desmos even says. It says it's a 7-element list. It means it's a list with 7 data points, right? So y1, instead of saying equals, if I want to do regression and I want to fit data to a mathematical function, I use the tilde key instead of equals. Tilde is the one that's to the left of 1. You hit shift and then it's to the left of 1, and it's that little squiggly line. Everybody get that? So y1 tilde, now I'm going to type in my m because I want to fit this to m. M is going to be one of the parameters. I'm going to let Desmos figure out what the best value of m will be. And then I'm going to multiply that by x1. So I'll type x1 and then plus b. Okay. So again, I'm just going to match it to slope-intercept form, but instead of an equals, I use a tilde. And instead of x's and y's, I use x1 and y1. Now look what it gives me when I do that. It does some really cool stuff. It creates the best fit line, first of all. All right, that is the best fit line for that data right there. That's it. Using this process, it's a statistical algorithm called linear regression. What does all this stuff mean? All the information it gives to me over here. Well, let me take a picture of this and we'll just focus on, I'll blow it up a little bit. Can I make that bigger? A little bit. Okay, so for just a second, let's look at this. That stuff right there, what's that mean? Well, the M and B are pretty obvious, aren't they? M is the slope that the math gods calculated when they did regression, and B is the best y-intercept for that, for that line. Those are the M and B values. That's pretty self-explanatory. What does this stuff up here mean? Well, R is what we call the correlation coefficient. It's telling me how strongly does the output correlate with the input. If it's a positive number, then that means it's a positive correlation, that if I increase the input, the output increases also. In this case, as time increases, the speed increases also. Now, if it were doing the opposite, if this object were slowing down and as time increased, the speed decreased, then R would have been negative. That would have been negative correlation. They're moving in opposite directions. Okay, so that's what that R means. That's the correlation coefficient. Let me make a note of that. How about? And you guys remember talking about correlation? Like if you had a scatter plot and this is your data, if it's doing this kind of thing, so the best fit line has a positive slope, we call that positive correlation. If you have a data plot that looks like this, where the best fit line has a negative slope, that's negative correlation. And if you have something in the middle, where the data is just random and it doesn't seem to have any pattern at all, then that's no correlation. So the correlation coefficient is R. R squared is a really important number. R squared tells us the strength of the correlation. And you can think of it almost like a percent. So if I turn that decimal into a percent, it looks like 93.74 in this case. That's about how good the fit is. 100% fit would mean every data point fell exactly on the best fit line. 0% would mean it's just totally random. Totally random. It has no predictive ability at all. This is pretty good. 93%. I mean, that's an A, right? So when we look back at this data, and it makes sense that this is an A, if you want to talk about it that way, because you can see that's pretty linear, right? That fits a line pretty well. Okay, give me a 1 to 5 so far. Does that make sense, what we're doing? Okay, so now what can we do with this? We can use this as a model in a really powerful way. Look at the second part of this question. It says, find the linear regression model and use it to predict the velocity when t equals 8 seconds. Well, let's start off. Let's make a prediction what the velocity should be when t equals 14 seconds. How about? Let's try that one. Okay. Well, the data point that we got when t was 14, the speed was 34.5 meters per second. Okay. I'm going to use this model and I'm going to see what it predicts. Not what the data was, but what the model predicts it should be. To do that, I would just plug the value 14 into this regression equation. But in Desmos, I have the ability to do that very easily. I can turn this into a function. So I could write this as f of x. I'm going to use function notation. F of x equals mx plus b. And look, it's the same exact line, isn't it? Right? Because m and b were already calculated above when we did the regression. So big deal. What did we just accomplish? It's the same darn line we just had. True. But now this is a line that we can do something with. With the black regression line, I mean, I could drag a point along that and see what the ordered pairs are, but I can't plug in specific values. It's not a function. I can go down to the red function that's written using function notation. And if I want to figure out what the output is when I input a 14, how would I do that, everybody? You guys know that. Say it again. X equals 14. So I'm going to say f of 14 then, right? I'm going to replace the x with a 14. F of 14 is 44.96. So if we round to one place, it's 44.5. Okay, 44.5. Now that's different than what was predicted. And let's graph that point. If I create an ordered pair in Desmos, it'll interpret that as a point. So we're going to put in 14. And I don't even have to type out that long decimal for the y value. I'll just put f of 14. And look what we get. And I'm going to make that a different color so that one stands out a little bit. How about, let's make that, how about purple? Okay, I'm going to put a label on it so we can see the ordered pair. Now let's compare those two. Which do you think is better? Which do you think is better here? And everyone look up and focus on this. This is an important question. If we were going to run this experiment again with the exact same object, would you feel more comfortable predicting that when the time is 14 seconds, we're going to get the speed that we actually measured last time, or the one that's predicted by the model? Okay, let's vote. How many people would think the actual measurement is a better guess about what's going to happen next time? Okay, 1, 2, 3, 4, 5, 6. How many people think the model's a better measure? Anybody? No takers on the model? Too bad, because it's a lot better measure. The model is more accurate. How come? The measurement seems like that's what we measured. That should be more accurate. But anytime we measure something, what happens with an actual measurement? Are they always 100% accurate? No, they're not, right? There's going to be some measurement error. There's going to be some little variability in the experiment. What this serves to do, this best fit line, is it kind of averages out all that error. And it creates a model of what should happen in an ideal situation. Here's a way to illustrate that. Click and close for a second and think about this one. This is you'll like this. I think this explains the concept really well. So if I gave, if each of you guys, if you flipped a quarter 10 times in here, let's say, on average, what would you expect to happen if you flip a quarter 10 times on average? How many heads and how many tails would you suppose? 50-50, so 5 and 5, right? Okay, would it be crazy if you all flipped a quarter 10 times, and let's say Ben got, I don't know, 1 head and 9 tails? Would that be absurd? I mean, that could happen, right? If we let everybody in here flip a coin, there's going to be some cases where you're going to get on a streak and there's going to be a lot of heads or a lot of tails, right? That could easily happen. Or let's just say, how about 2 and 8? 2 tails and 8 heads or something, right? Okay, now imagine this. If you flip a coin 1,000,000,000 times, so that's a lot, right? It would take you, I don't know if you could even do it in your lifetime, but if you flip a coin 1,000,000,000 times, you probably could. Flip a coin 1,000,000,000 times, would you think something was rigged with the quarter if you got 200 million heads and 800 million tails? Okay, that could never, ever happen. It might as well be impossible. You could flip a coin, you could do that experiment a trillion times, and never once would you ever get 200 million heads and 800 million tails. Statistically, it just can't happen. It's going to end up being about 50-50. When you flip a coin 10 times, you don't see that. I mean, then that's a small number of individual flips, and you can get kind of bizarre things happening. Like if I flip it twice, it'd be no big deal to get 2 heads and 0 tails, right? But as you flip it more and more times, the law of averages takes over, and you start to see averaging out of the individual variations in flipping a coin. And sure, you might end up, are you going to get exactly 50% heads and tails? No, certainly not. If you flip it a billion times, you might get 500 million and 40 heads, and would that be 499 million 960 tails? I mean, there could be small variations, but over the course of a billion flips, 40 heads, 40 extra heads is going to be nothing, right? That's going to be just a tiny, tiny, tiny fraction of 1%, not even close to anything that's barely measurable, right? You see my point? When you do things many, many times, you average out the error. So what we've done here is we've taken all these data points, and by creating this linear model, we've kind of averaged out the error. So the model is a better predictor of what would happen next time than the original data was, a much better predictor. Okay? Give me 1 to 5 on that. Does that make sense? Okay? All right. So that's one really important way we can use this mathematical model. Let's look at another example. Okay, how about this one? Table below shows the average price of a movie ticket based on the year. Okay? Find the linear regression model and use it to predict the year in which ticket prices will first reach $100. Okay, so let's create this. Now, when I create this data table here, where do I want to start my t values? Do I want to start at 0? Probably let's start at 2012. We'll define t as the number of years since 2012, right? Otherwise, you see why that's the case. Otherwise, if I were to put the data in just like this, when I look on the XY plane, it's not very convenient to have to go clear over to 2012 to start seeing data points, right? We'd rather have the data points close to the axes where it's convenient. So we'll define right away, we're going to say something like this. Let's let t equal years since 2012. So the first year would be what year? Well, years since 2012, 0. There we go. First year would be year 0 exactly. Okay, so, or I'll tell you what, let's do, to make this even easier for us to go way out, that would be fine to do. But how about if we instead make these the years since 2010? So it's a nice round number. Either way, as long as we are consistent, it doesn't really matter. We're going to get the same answers. Okay, so let's put this data in. You guys try this. I'll go ahead and kind of work here, and you can compare what you're doing to what I'm doing if you're unsure. Oh. Oh my goodness. Okay, there's your data. Create a data. And you can use the old data table if you want to, or you can clear it. It doesn't matter. Okay, that doesn't look very good there, does it? So what should I probably do to resize that so I can see it better? Yeah, good. I'll click on Zoom Fit. There we go. That's better. Okay, and what do we get here? Well, I used X and Y. Let's go ahead and change it this time to T and P. How about? Which means I need to go down and change this. I need to go down and change my regression equation then. Instead of a Y1, that would be a P1. Instead of X1, that would be a T1 if I change my variables. And there you go. Okay. So is this as good a fit as the last one? Not quite, is it? This is only an 89.6% fit. So it's a B plus. Not bad, right? But it doesn't stick to the line as well as that last data did. And then if we want to make a prediction here, let's go ahead and turn this into a function. I'm going to call this P of T equals MT plus B. And there's my line. Okay. All right, now how am I going to do this one? This is a little bit different, right? If I zoom out a little bit here, my input, oops, I don't want to do that, I guess, did I? Let's do, there we go. So my input is T, my output is P. It's not asking me for a specific input value. It wants to know, when is the output price going to be 100? What can we do? We did some stuff like this in Unit 2. If I want to know what input gives me an output of 100, what was my trick? Say it again. I'll just do, I don't even have to do P of T. I could just say like Y equals 100 or something. I just need to draw a horizontal line that has a Y value of 100. Okay. So I'm going to call that Y equals 100. Now I've got to zoom out quite a ways to see that, right? There it is. Okay. There's my horizontal line. Every point on that line, if I drag across that line, if I, what do you call that? If you trace along that line, all the Y coordinates are 100, aren't they? Okay, the one I'm interested in is that one right there. Okay, what's that telling me? Yeah, it's going to take over 500 years after 2010. It'll be 504.4. So it's in the 504th year. Now, we haven't quite gotten to 505 years later. So 2010 plus 504, man, what do we get there? 2514. The year 2514 is when this model anticipates that movie prices will first reach $100. Okay, how about that? What do you think? You buying it? Which do you think? How come? What's your thinking on that, Thaden? If we compare this one to the last example we did, the last prediction is probably much, much more probable than this one. How come this one? I mean, it's a model and it's better than nothing. But why do you suppose this prediction is very iffy compared to that last one, which was very solid? Say, okay, well, okay, so the regression wasn't quite as strong. Even if the regression was as strong, though, does something seem a little bit fishy about trying to make a prediction way out here for a data set that's way back here, right? You see what I'm saying? I mean, like any small variation in that line, if I'm going 500 years into the future, even a small variation in that slope is going to make a huge difference, isn't it? Like, look what happens. Let's, here, I'm going to keep this line here. I just want to demonstrate something. So let's graph the line. Let's see, Y equals, I'm just going to use these values for M and B and recreate that line. So Y equals 0. Can I cut and paste that? No, I can't. Bummer. 0.183214x plus 7.5 58107. Okay, good enough. Now let's go back up here. What if I change one of these data points even slightly? Like, what if that last data point, I'm just going to change it to 9.04, barely any difference, right? One data point. Look what it did to that line. If I go all the way out here to 500 and, whatever that was, 504, that's a fairly big difference in what these two lines predict for ticket prices, right? You see what I'm saying? Like if I create, here, let's do this. If I go out to, you remember what that value was? It was 504.43 or something, right? Okay. Let's look at those intersections. Okay, there's $100 for the first one. This other one's predicting, that's a decent ways off, right? $4 off. I mean, so we really can't. It's hard to tell when you extrapolate, when you're going to move really far outside the data set instead of interpolating, which is what we did in this last example, right? In this example, we were interpolating where we were trying to pick a data point that was inside the data set. Well, yeah, 14. When we picked 14 in that last example, oh, that's the wrong one. That one, right? Oh, I thought I had a picture of that. Did I not? Maybe I didn't take a picture of it, darn it. But that last example we had, we were picking a data point to make an estimate about that was inside the data set. That's pretty safe, right? That data was hugging that line pretty well. Any small changes in any one of these data points would not have really very, very dramatically impacted what the slope of that line was going to be. The predictions would barely have changed at all. It's only when you get way the heck out there, right, way outside of the data set, that your predictions start to be a little suspect. Okay, give me 1 to 5. Do you get what I'm saying there? And this, so what are you going to do with this? Not much. I'm probably not even going to test you on this stuff. I just want you guys to see this because it's real world math that someday you're going to do. Okay. Anything else? Let's see. No, then this is stuff we already did. We don't need to go through all this stuff. Okay, I'm going to put up a little assignment and just let you guys practice this a little bit. Just mess around with the technology. Okay, and I will grade the assignment, but again, I'm not even sure I'm going to put this on a test. Okay. Whoops. Okay, this is going to be assignment 2.4. And I want to change it. There's a couple problems I want to just looking at this, want to edit just slightly. So I'll fix them during my prep next period, and then it'll be up ready to go. There's one other thing I want to show you guys that, again, I don't think we're going to test over. That's just interesting.